And a couple of professors at the university decided that even though they didn't know anything about battery technology, they could get in and learn because the electrolyte was beta double prime alumina. And Bryan just happened to be able to get in on the ground floor of what has become a huge area today of battery technology and made some very intricate parts that were used for a company called Ceramatech, which was making the sodium sulfur battery. Bryan got an MBA and was a plant manager as this company transitioned from battery technology to also start working on zirconia, which is used for all sorts of wear parts and later on as solid oxide fuel cells. Bryan decided to go to what became Saint-Gobain, Norton in Boston, and worked on silicon nitride. While he was there, he had the opportunity to work in Connecticut on silicon nitride ball bearings. And these are world-class ball bearings that were used in all sorts of applications. From the East Coast, he transitioned to the West Coast and worked for Applied Materials, a semiconductor house that was a supply house. And he worked there until he was recruited to come to a company called America in Salt Lake City. And America at that time wanted to use zirconia as hip implants. And Bryan helped them see that they could get into silicon nitride. And they put a lot of effort into getting to silicon nitride, only to find out that those joints squeaked. And no one likes a squeaky hip joint. And they were able to transition to working on back implants, neck implants, and on antiviral applications. So Bryan's had a great journey. He's never stopped learning. He completed a PhD at the University of Tokyo and is a prolific inventor. And he's a fellow of the American Ceramic Society. We are so grateful to have him here today, and you'll be delighted to hear his, as he takes us on this journey about silicon nitride. We welcome Dr. Bryan McEntire.
I'm kind of soft-spoken, so I'll try to put this up close so you can hear me. Okay, and sorry for the screen issues here. You're going to have to pay attention to your right screen mostly to get the full impact, but if you want to see some close-ups, the left screen is where you need to go, I guess. Thanks, Raymond, very much for that kind introduction. And it's really a pleasure to be back here on campus after actually a 42-year absence from being here. Wow, have things ever changed? You know, there was this big open space between Merrill Engineering Building and the Union Building, which is no longer the case. It's just amazing. So I'm going to talk about silicon nitride and kind of a material that's occupied my career for a better half of the past 36 years. And I call it from lab to life because I think during my entire academic career, it's actually come to life. And so we'll see how it goes. So before I begin, I have to actually acknowledge that I've had the opportunity to stand on some shoulders of some really great professors here at the University of Utah. Raymond's father was one of the key individuals who kind of changed my life when he actually, Ivan Cutler, told me to, hey, you should look at ceramics, because I was going to go into polymers. You know, I'd just seen The Graduate starring Dustin Hoffman, and plastics was where you want to be. And Ivan convinced me that I should look significantly into ceramics. So I had my introduction to ceramics from him. And then I had physical chemistry from Henry Eyring. One of my key professors whom I later became an employee of with Dr. Ronald Gordon. He taught me thermodynamics of solids. Professor Anil Virkar, who's still on the faculty here at the U, I had crystallography and X-ray diffraction from him. And then Frederick Hertzberg in my MBA program actually taught me organizational management. And I'm really grateful for these individuals, and all I can say to you is I hope you get the same sort of love and fellowship and leadership and mentorship, I should say, from the professors who you interface with. And there are actually many more, but I've just highlighted these few. Okay, so here's my overall outline. I'm going to talk about the history of silicon nitride a little bit, and then discuss its chemistry and processing, review its physical and mechanical properties. And then I actually spent about 16 to 18 years, as Raymond mentioned, in industrial and aerospace and automotive and even electronic applications of silicon nitride. But for time constraints here, I'm going to focus on what I've spent mostly the past 20 years on, and that's a discussion of orthopedic applications of silicon nitride, and then I'll summarize. Okay, so here's an overall history of silicon nitride. Actually, it's a material that has intergalactic origins, but there is no native mineralogy of silicon nitride. You can't go dig it up out of the ground. It was first synthesized in 1857, and it was considered to be actually the perfect fertilizer because by weight it contains 40% nitrogen. But unfortunately, its dissolution kinetics were fairly slow, and it was fairly expensive, and there are other materials that came along that turned out to be a little better in terms of fertilizer. Its crystal structure was indexed first in 1879 as alpha silicon nitride, and the first process patents for actually carbothermal reduction of silicon nitride were granted in Germany in 1896. Its first application as a refractory occurred quite a bit later, over 50 years later, in 1952 here in the United States. But it really took off when Lang and co-workers actually learned how to take this material and densify it by adding various synergy additives, and that occurred in the mid-70s. And that spawned some huge government programs of which I was the participant and actually had a couple of the largest ceramic subcontracts that I was the principal investigator on when I worked at Norton and Norton Tier W in the 1990s to develop it for heat engine applications. There are three programs, in Europe, United States, and Japan, all of them focused on this. But the first actual implants for biomedical applications took place about the same time in 1986. And then it wasn't actually cleared as a medical device here in the United States until 2008. Okay, this shows you over my academic career kind of the number of citations that have occurred if you just go to Google Scholar and look up silicon nitride and see how many hits that you can get. If you go all the way back to the 1960s, you get around 40 to 50 papers per year. And that corresponds or contrasts to in last year, which was well over 15,000 papers that had citations associated with silicon nitride. So you can see the overall growth. And it's in all various sectors and segments. So it's a tremendous field to get into still, because it's still expected to grow significantly. You can actually see that here on this next slide. So what are the markets for silicon nitride? There are actually 4 or 5 major markets. The world market itself is estimated to be about 1.2 billion in 2021 and is expected to grow to about 2.2 billion by 2030. In industrial, bearing components, as Raymond mentioned, is one of the largest, and I ran the largest US bearing factory for silicon nitride in Connecticut. for a number of years and just totally loved that particular operation until I got into the electronic side of it and went to California. But there are also cutting tools that are an important part and other wear parts. In aerospace, it's also really bearing components and various actuators. They take advantage of the weight difference that silicon nitride has. So every airplane that you fly on, modern day airplane, the flap actuators in it are actually have silicon nitride parts in them. All of the bearing components and the rods and push rods and everything else. It's fairly low stress, but quite an effective operation for silicon nitride. So semiconductors are expected to be a high growth area for silicon nitride, particularly associated with power modules. And in biomedical applications, the only product that's really been approved or cleared by the FDA at this point in time has been spinal spacers, which I'll talk about a little bit later on. But there are significant developments in a whole lot of healthcare-related areas. Okay, so in terms of the crystal structure of silicon nitride, there are really two relevant forms. There are actually three phases, but two of them are commercially relevant. They're alpha silicon nitride, which is shown on the left, and beta silicon nitride, which is shown on the right. The alpha phase is what is generated in basically a powder form, and it irreversibly converts to the beta phase upon heating above about 1500 degrees C. So it becomes a stable phase at room temperature, even though both alpha and beta they're both stable phases at room temperature. One of the interesting things about the beta phase that relates to its microstructure is actually the tetrahedra that form the unit cell has a big open space down the middle, a channel. And this channel serves as a diffusion path for ions to move in the C-axis relatively easily. And that actually advances its ability to be sintered, particularly when you add additives. And secondly, it elongates the grains in the C-axis, which gives the microstructure a fibrous nature to it, which is important for its overall mechanical integrity, which I'll talk about here in a minute too. Okay, to make silicon nitride powder, there is basically three methods that have been developed. The most traditional method that was invented very early on is basically direct nitridation of silicon. And this is where you take very fine silicon powder and you put it in a furnace and you cover it with nitrogen gas and heat it. And it reacts. You have to keep it below the melting point of silicon, so it nitrides and it forms agglomerates. You have to mill that back down, and then there's a washing and cleaning step that takes place. And most silicon nitride today is produced via direct nitridation. The second process is diamide decomposition, and this particular process is complex. It involves minus 80-degree reaction chamber where you take silicon tetrachloride and ammonia and react those together in a two-step process. But it forms an incredibly fine, very high-quality alpha silicon nitride powder, which is the most preferred material that's used today. And a company called Ube Industries has actually perfected this particular process and has all the patents on it, so they're the only ones truly in the world who produce it. And the third process is actually called carbothermal reduction of silica. So you take silica and nitrogen and a carbon source, you put them in a furnace together. This is an endothermic reaction, so it requires particular heat to get it to go. And in fact, Raymond probably knows this story, but his father actually developed a very low-cost method here at the University of Utah where he took clay and coal and combined those together in a nitrogen furnace to produce a low-cost silicon nitride, and made quite a splash at the time. But unfortunately, carbothermal reduction has kind of taken a back seat to the other two processes, although there is one company, Toshiba, that still claims to have capabilities to produce it. It seems like they only use it for their in-house needs. So this is what the raw materials look like as they come out, and I've highlighted just kind of in a couple of areas. One is the overall alpha silicon nitride content and the surface area of these materials. You can see that most of the companies who produce this produce it by direct nitridation, so they're just reacting silicon and nitrogen. And as I mentioned, Toshiba is the only company that I'm aware of that has capabilities still to do carbothermal reduction, even though Dow Chemical and a couple other companies invested heavily in it, it never took off. And of course, Ube Industries has DEAMP and decomposition. The important thing about the quality of the raw materials is they're very high purity materials, and they have very high surface area. They also have very high alpha phase, all of which are very important to produce good quality components that are readily sinterable. Okay, so once you have the powder made, how do you fabricate the material? Well, most conventional ceramic processing methods can be used for silicon nitride. And in fact, there's a lot of activity on advanced methods, 3D forming of silicon nitride these days as well. So, you know, the typical processes you'll see in any sort of ceramic manufacturing operation. The one that I was originally responsible for here in Salt Lake City is a powder press, mill, and furnace, and then you get the devices. But one of the unique things about silicon nitride manufacturing is the densification process itself. So there are actually 6 methods of densifying silicon nitride, because it is a difficult material to densify, and it took quite a while, almost all of the 80s and 90s, to learn how to appropriately densify it. So let me just quickly go through those. So the first method that was used is called reaction-bonded silicon nitride. So this is similar to actually nitrided silicon nitride, but you form a compact of silicon, and then you nitride the silicon compact to form a device. It has very low shrinkage, but also reasonably high porosity in it and very low strength. Produces nearly net-shaped components. So it's good for refractories, and that's what it was originally used for. The next method that came along was, of course, hot pressing of silicon nitride. And the interesting story behind this one is this also has a Utah connection. Dave Richardson, who is a graduate of Utah, went to work for Norton Company, and he came up with, along with a colleague there, a formula for a sinterable, a hot pressable silicon nitride called NC132, which became the standard silicon nitride by which every other silicon nitride was judged in the 1970s and 80s and 90s, and still even today it's produced as a particular material. But the unfortunate thing about hot pressing itself is that it's fairly simple shapes, and there's a lot of machining to be done if you want to actually use it. So the next method that came up was called sintered reaction-bonded silicon nitride. And the sintered reaction-bonded process is kind of a takeoff from reaction bonding, except this time you mix sintering aids into the silicon powder, and then you react it to form it silicon nitride, and then you take it up to much higher temperatures to actually densify the material. So this proved to be very effective in terms of increasing the strength and density of the materials, and it allowed you to produce complex shapes. I will say that Kyocera actually has, I think, perfected this particular process for some of their devices. And then proceeding on, the next one was actually sintered silicon nitride. So people said, okay, we need to figure out how to sinter it at ambient pressure conditions without hot pressing. And so this actually took the form of more additives, a lot of experimentation in the 70s, 80s, and 90s on this. But the unfortunate thing about this, it did give good properties. particularly at room temperature, but not necessarily at high temperature. But the problem with it is that the process defects kind of started to show their head in this, and you got basically materials with fairly low Weibull modulus, or reliability in this case. So the takeoff from that is they started applying pressure to the sintering process. And so there was a process developed called gas pressure sintered silicon nitride. And this is where they would apply a certain amount of pressure during the densification process. This would contain and prevent decomposition of the silicon nitride during the process. They had to go to fairly high temperatures. But they would get then materials that would have reasonable strength and fracture toughness, therefore good reliability and good density. And then the last one is, of course, hot isostatically pressed silicon nitride, and this is where you take very high pressures and apply that to actually pre-sintered components to basically squeeze them to remove the porosity and remove the defects, and that's basically what the facility at Syntex here that I oversaw was using to produce this material for biomedical purposes. So all of these processes still remain fairly active out there in terms of methods to produce silicon nitride. And in fact, this is just a couple of photographs of the ISO 13485 facility that's here in Salt Lake City. And I had the distinct pleasure of setting this facility up and kind of overseeing it for about 20 years. And it's been a lot of fun, along with my colleagues who are here, which I appreciate. Okay, so let's talk a little bit about the properties of biomaterials here, just to kind of contrast them and accentuate a little bit about the differences and what's going on with silicon nitride. And I've highlighted here 3 particular areas: flexural strength, or strength itself, elastic modulus, and fracture toughness values. And I've just shown 3 particular ceramic materials: alumina, aluminum matrix composite, which is also known as zirconia toughened alumina, and silicon nitride. 2 metal components which are in common use: cobalt chrome and titanium. A plastic, which in this case I highlighted was PEEK, polyether ether ketone. And then on the far right over there is the properties for cortical bone, because all of these materials in some way or another have to interface with bone structure itself. So the most apparent thing that you can see if you contrast and look at all of these things is that the ceramic materials actually have the overall lowest fracture toughness, particularly when you compare it to the metals. So they're brittle materials, and they fail that way. They fail brittly, they fail by crack propagation. But note that alumina has a fracture toughness which is essentially half or even a quarter of that of either ZTA or the silicon nitride material. And we're going to explore a little bit why that is the case. But these materials, the ZTAs and the silicon nitrides, are really the ones now that are a focus because of the fact that they can increase toughness a lot and they have very good strengths comparable to the metals that are out there. Well, of course, the metals fail by yielding, but ceramics fail actually by fracture. The other important thing to look at is the elastic modulus of the material. Ceramics have very high elastic modulus. The metals also have a high modulus as well. So the reason PEEK is in here is that it is a material which has a modulus which is in the range of bone. And why is that important? Because if you're trying to interface with bone, you want to prevent what's called stress shielding. That is, the device that you're putting in conforms to the tissue or the bone surface that you're applying it to. So that's why PEEK has become a very popular and important implant in the industry. So I'm going to dive into now just these 3 materials, these 3 structural materials a little bit more, and talk about, let's look at their microstructures a little bit. So here's a microstructure of alumina. You can see it's basically an equiax structure, so kind of rounded grains. So if you're actually a crack and you want to propagate through this particular material, how easy do you think it might be? Well, it's pretty darn easy because it basically follows the grain boundary and it just moves right along. So that's why its overall fracture toughness is pretty low. It has lower strength because of that, because of the equiax strains, and it has a low resistance to crack propagation. So they came along with zirconia and zirconia-toughened alumina, which is this microstructure here. Now the dark phase in here is alumina. The lighter phase here is zirconia, but there's also a strontium aluminate phase in here, which is actually a fibrous type structure, kind of right there, which was in this particular material was engineered by Ceramtech in Germany. And what's the unique thing about it? Well, it looks like it has equiax microstructure as well too, but what happens when a crack propagates through it? As a crack propagates through it, it also follows basically grain boundaries, but in this case, as the crack propagates, it triggers a transformation in the zirconia grains around the crack that invokes a volume expansion of those grains from a tetragonal phase to a monoclinic phase of about 4%. And that volume expansion actually puts compression around the crack tip as it propagates. So it tries to hinder the crack from opening and moving by this compression particular method. So it has higher strength in ZTA because of this transformation that occurs in the material. So now let's contrast that to, say, silicon nitride. So here's a silicon nitride microstructure. You can see now it's, instead of equiax, it's very fibrous. Some of the grains are, the C-axis is perpendicular to the plane that you can see, and some are parallel, so you can see what it looks like. So you can have these elongated kind of fibrous-like grains. So this, as cracks propagate through this intergranularly, it's a very tortuous path that they have to actually follow as they go through. And what happens is that some of these grains actually bridge over the crack and keep it from expanding. So, and you can see that in this particular stress analysis, which shows that there's compressive stresses around the wake of the crack as it proceeds through the material and at the crack tip, because you have these bridging grains and you also have deflection that occurs. And this what gives silicon nitride its strength and toughness. Now, the interesting thing here is, and what I have to point out is this is a mechanical-based toughening mechanism, as opposed to the zirconia material, which is a chemical phase-based toughening mechanism. And to accentuate that, what I'm going to show you here is a study which was performed to look at basically indentation toughening of three materials: alumina, which is this low material here, zirconia-toughened alumina, and silicon nitride. So these particular curves represent crack resistance, or what's called R-curve behavior. And R-curve behavior is the resistance to continued propagation of a crack as it begins. So it says as the crack begins to extend and grow, the resistance actually increases, particularly in silicon nitride, because of the fact that it's being constrained by these bridging grains. But so is the ZTA material. But remember the difference in between the two? So one is a mechanical based and the other one is a chemical phase or physio-based. So what happens if you take the as-received component And before you actually do the testing on it, you subject it to an environmental condition called hydrothermal aging. So hydrothermal aging has been known to actually affect the transformation of the zirconia. So the zirconia that's in the ZTA transforms, and when it does, it actually reverts to where it was originally, which was basically alumina as a material. So there are distinct differences between these materials in terms of their toughening mechanism. Now, this is well recognized, and even the manufacturer of this material, Ceramtech, has published extensively on this. And they claim that, okay, well, at the surface of the material, if in fact you have a lot of transformation taking place, that does not suggest that the reliability of the material is lower, because it takes a very, very long time for that hydrothermal degradation to proceed to a point where the component would actually fail. But remarkably, this particular material has only been on the market now for about 20 years. And if you do the extrapolation of the data, you might start to see in the coming years some of these failures occurring. In fact, I think I keep up on the literature on this and begin to see there are a number of failures that are actually occurring out there right now. So it's actually like femoral heads, they just fracture in half or in multiple pieces. Anyway, so my point is that silicon nitride is a material that is at least as reliable as the current standard out there, which is in fact the ZTA material. Okay, and this slide just highlights that. An early study that was done shows that if you take silicon nitride and you subject it to autoclaving conditions for an extended period of time, up to 100 hours or more, that there's no change in phase composition, and the strength of the material basically remains constant associated with that. Okay, so let me, after talking a little bit about that, I want to jump into some of the orthopedic applications and kind of put out there why I think that silicon nitride as a material is something that'll be in your future. Hopefully it'll be in my future as well as a biomedical material. It is already in one particular product, but I think it'll be in a number of more. So the first one I want to highlight is, of course, hip arthroplasty. So this is what if you were to go in for a hip surgery, this is what you would get. You would get a modular device, which includes a stem, a femoral head, a cup, usually plastic material, and an acetabular, should say this is a liner, and an acetabular cup that fit into the acetabulum of the hip. This particular device was pioneered in the 1960s and early 1970s by Sir John Charnley in England. Before that time, they had basically non-modular particular devices. But there's been a recent series of meta-analyses that have been done to look at how good was John Charnley's hip in the 1960s and 70s compared to hips today. And you can do that by looking at the survivorship of these particular hips. That is, how many of the patients who receive these have to go in for revision surgery? And here's what that data looks like. So this is John Charnley's hip here, and the survivorship before first revision was well over 80% for a 25-year survivorship. So that means if you put it in, it would last, it had 80% chance. Whereas today, or actually just a few years back, it's significantly lower than that. So isn't that a sad case of what's happening in the industry? I do think so. So why is that? Well, if you look at the reasons for failure, the failure causes are actually all the same that happened with John Charnley. They're fracture, they're wear, corrosion, osteolysis, which is death of the bone next to the implant, infection, and infection and aseptic loosening often come together, and dislocation of the device. And in fact, let me just show you one additional kind of interesting. So this is some data that I dug up from some of the publications that are out there that show different devices, their survivorship by year. And where does your eye immediately go to? It goes to obviously the red line, which is actually a device called a metal on metal. That's where you have a metal head on a metal liner inside a cup. And this was something that was really released in the 1990s. So this is fairly recent. And how could this be that actually they allowed this to happen? It's a sad case on what happens, and the problem is that there has been a lot of experimentation on basically patients in hip arthroplasty, but fortunately, as these curves show, more and more physicians are focused on going to ceramic-based components as opposed to using metal-based components. So the switchover has occurred, and most femoral heads now, except for the extreme elderly patients, now tend to be ceramic heads. And the reason is they, as the prior slide showed, they present better survivorship over the long run. Okay, so I pointed out the reasons for failure. So one of them is fracture. So the FDA has actually set a standard for components in terms of fracture, and they've done it at what's called various offsets. So in the modular design, offsets are things which allow the physician to adjust the device to make sure that the leg length of the patient is equivalent, to his other leg. And so it depends on how far in the modular head that you push the taper. And so they have different offsets, and the most severe offset is, of course, a 12.5 offset. But for these various offsets, there's a different stress that the ceramic can experience associated with the offset. And in fact, so these are data for silicon nitride, unfortunately unpublished data, but show that silicon nitride has the capability of meeting even the broadest range of offsets. So suggesting that it has very good viability as a femoral head in terms of fracture problems. And of course, I mentioned earlier that it doesn't have the degradation problem that ZTA has. So with its mechanical fracture toughness mechanism, it should last a long time. And the second major area is, of course, wear and osteolysis. So this is my recent data, which, again, the FDA requires that you take a predicate material, in this case it was a zirconia toughened alumina, and you, in a hip simulator, you look at the wear of the device, and this is wear against ultra-high molecular weight polyethylene. And what you're seeing here is the lower curve, it means more wear, so that's greater loss of mass. The upper curve is lower loss of mass. So silicon nitride actually, in this case, for this 5 million cycle test, outperformed ZTA at every time point that was examined, although you can see by the error bars that it wasn't statistically significant, but it did show that it was basically equivalent to the predicate. So my case here would suggest that silicon nitride should be a good material, very comparable to the standard that exists out there already. But that's not the whole story. So one of the experiments that we had the pleasure of doing is we wanted to look at subjecting the polyethylene to hydrothermal oxidation. So many people think that these ceramic materials are completely inert, that there are no reactions that occur at the surface of them, but there are reactions that occur. And these reactions can either dissolve certain portions of the femoral head itself, or they can affect actually the polyethylene as well. So this was a very simple experiment. We just took a polyethylene liner, it was a very advanced polyethylene liner, and we cut heads of 4 different materials: zirconia toughened alumina, an alumina, a zirconia, and silicon nitride. And then we had a standard in there, which was a polyethylene on polyethylene. And then just put it in the autoclave at 24 hours for 121 degrees C to see, is there going to be any sort of physical or chemical changes that occur in the polyethylene during this particular short duration test? And that was examined by using XPS and Raman spectroscopy. I'll just show you the Raman spectroscopy results. So the Raman spectroscopy, we could focus down to different layers and different depths into the polyethylene. And on the right side, it shows actually the overall results. So here are the materials that were tested. So they were poly on poly, which is a control, poly on silicon nitride, poly on ZTA, and poly on alumina, and poly on, in this case, zirconia. The bar graphs here show on the left side the oxidation of the material, and on the right side, the oxidation index. There was the degree of oxidation or the depth of oxidation. So I should say that polyethylene wears by embrittlement, and that is oxidation that embrittles the polyethylene and it chips out. So it shows that actually these materials that are oxides actually contribute to oxidation of the polyethylene, whereas silicon nitride in this case was very close to the control itself. Yeah, before I go there, I just, so what's the mechanism here? The mechanism is that actually slight dissolution of the aluminum or the oxide surface actually contributes to oxygen pollution into the tribal layer, whereas silicon nitride, its reaction actually acts as a getter of oxygen. So it has this protective effect. So this is all just short-term data. Hopefully it'll yield a long-term proxy to improve performance and longevity of these devices. And lastly, the most current problem that exists out there in terms of the reason people are going to ceramic over metals is fretting corrosion. So if you have a particular femoral head that's, in this case, a metal, cobalt chrome on a titanium stem, you have an electrochemical couple here between these two, and with slight pressure and motion, you get actually fretting corrosion that occurs, and that fretting corrosion products actually fall into the joint space and create all sorts of problems, including pseudotumors, what's called metallosis. I've seen operations where they open up the patient's hip and leg, and there's a great big pseudotumor there that's on the order of an orange or a grapefruit, that they have to pull out. And so this is a major problem. Ceramics, in particular silicon nitride, they have 1/5 the overall corrosion characteristics of these metal-on-metal couples. So that's another reason. Now I searched for data to do comparisons on ZTA versus silicon nitride, but right now there is no data out there that I've been able to find that would suggest how does silicon nitride compare to ZTA. I would suspect they're probably pretty close to being the same. Okay, now I want to talk about the other application, which is the one that has been cleared for use, and that's spinal fusion devices. And this is what this looks like in schematic form, or side view. You have two particular vertebrae, and you have in it a diseased or damaged disc or collapsed disc that is excised, and it's replaced with actually a spinal spacer, which is originally was allograft or autograft, and subsequently became allograft, and then became an abiotic material. And you pack bone graft around it, and what you actually do is fuse these two segments together. There's a lot of hardware that goes into this as well to stabilize the joint so that it doesn't move. And what this does is it takes pressure off the nerve roots, so that it reduces the pain significantly that the patients have. And spinal fusion surgery has been one of the fastest growing orthopedic surgeries out there for the past 10 to 15 years. It's not quite at the level of where hip arthroplasty is, but it's growing fast in this regard because it is deemed to be an effective procedure to actually reduce pain, and I'll show that here in a minute. So I just want to point out the changes that have occurred in spinal fusion devices. So if you were going to have spinal surgery back in 1998, the only way you would do it is using what's called autograft. That is, the surgeon would go in and cut a piece of your acetabulum out, and then he would carve that up in the operating room, and then put that into your, after you excise your natural disc, he would put that in as a spacer. That's a pretty painful operation, actually. So that's why that kind of went away. And then they went to allograft, and allograft is cadaver bone, so it's dead bone. So they harvest the bone, and then they machine it, and they sterilize it to a certain extent, but it still has some biotic capability, so they thought that was good. But of course, it's in quite limited supply. But you can see that it was about 60% of all cervical cases then. And then by 2018, this had switched all over to abiotic materials, including PEEK and titanium as the primary materials. And they were about 70% of the overall market at that point in time. The unfortunate thing about these, and particularly about PEEK, is it's basically totally inert. It doesn't interact at all. There's no biological efficacy. There is some with titanium, but kind of not a whole lot there. So where is it going in your generation? And it's either going to these composite devices, which maybe is a combination of PEEK and titanium, or PEEK and hydroxyapatite, or we hope that silicon nitride might be a material there, because silicon nitride is naturally a material which is osteogenic as well as bacteriostatic, and I'll show that here in the upcoming slides. And in fact, that's where I'm going next, is to just basically show an early study which actually originated here at the University of Utah in the Bone and Joint Research Laboratory, where we wanted to find out how good is silicon nitride in terms of its osteoconductive behavior. So the study actually involved taking a silicon nitride bone plug here, which was a composite of a dense outer portion and a porous inner portion. And the porosity here on this material, which we called cancella structured ceramic, was about 72% porous. And it had an average pore size of about 450 microns. And this was then implanted in the femoral condyle of mature sheep, and they were ambulated for up to 3 months or so, and then 12 and 24 weeks. And then we, and actually Dr. Roy Blaybaum, whom Raymond may remember or know, did a lot of this work, he and his coworkers, and did the analysis. So I'm going to take you from this. This is the experimental design, and then we're going to take you to what's called the histology slides, which is the next one. I'll only take you to the 24-week histology, which this is a cross-section on one of the implants that came out of one of these sheep. So let me just walk through the phases here. So here's the ceramic. This is silicon nitride. This is also silicon nitride, but this is the CSC. So this is the porous structure. You can see here. The pink here is actually mature woven bone that has actually grown into the structure. The white here is collagen fibrils, or it can be porosity as well. And the blue in this, there is a combination of other tissues and osteoblasts that's actually promoting the growth of this. The yellow arrow down here that you can see is just to point out that there was very good what's called apposition of the bone to the ceramic itself. In other words, there was no fibrous layer in between the two. It just adhered right to the bone. And so the results were actually quite remarkable, and it showed that in this implant, bone had grown from both directions all the way through the implant by the 24-week endpoint, which was really fantastic to show that it really had great osteopromotive characteristics. So you can't really do that sort of testing in a human, but one of the things we could do is actually look at what's called retrievals of humans that have been in humans for a while and examine those. So this is a two-case study of retrievals, and one was a cervical implant of a 58-year-old male that had been retrieved after 11 months in vivo. And because of an anatomical change that didn't affect the implant, it was associated with the cervical plate. And the other one actually was then a peak implant, which was in a little bit older individual, but comparative, and in there for 11 months. And this was because this particular individual had persistent pain, what's called pseudoarthrosis. The implant had not fused well enough. And so we got these two implants and did sectional analysis on them just to see what was going on, and then published about them. This is what the explant looked like of the silicon nitride in the cervical. You can see that here's the implant itself, and this is what's called the graft hole, where bone is grown in and through the center hole of the implant. And there was also some bone on growth that was actually noted as well. And what we looked at using XPS and Raman spectroscopy is the change in the hydroxyapatite, and this is in the center of the implant. So here's the graft hole, here's the silicon nitride source, sectioning this in half, and looking at the implant and looking at various positions along the implant to see, okay, is there chemical or structural changes that are taking place to the hydroxyapatite? And yes, there is. You can see that as you look at the Raman spectra, you can actually see a Raman spectra that being depressed to a lower wave number close to the implant, and it goes out and then comes back in as you go across the implant. You can see that here in the other two graphs as well. So it says that what's happening is that silicon nitride is actually donating some of its ions, in this case silicon and nitrogen, and they're basically endocytotically taken by the osteoblasts and incorporated into hydroxyapatite. Now, it's well known that silica as a material is a very osteopromotive material, but these are among the first studies that show that silicon nitride is as well. So if you look then at the peak implant, which we did the same thing there, and first of all, you can see that there is not much in the way of very much integration of the peak implant to the bone. But if you look at the chemical and physical composition of the material, you see that there are actually no changes, which is what you might expect for in a particular material. So it really points to the fact that silicon nitride is osteopromotive. So now what happens here is that so slight dissolution of the surface of silicon nitride leads to the soluble formation of ammonia and silicic acid, which are then endocytotically incorporated into the hydroxyapatite by action of the osteoblasts. And so a very good osteopromotive characteristic. So the other thing that implants fail for is infection. So if you can somehow address the infection, that is another problem that silicon nitride could help on. So this is one of the first studies that was done to kind of examine that. This is in a Whistler rat study, and it's a calvarial study, so the calvaria is the head. And these are very teeny implants of peak silicon nitride and titanium that were implanted on the dura of the animal, and then the flap was closed. And these animals then were incubated for up to 3 months. But before they implanted them, they actually contaminated the implant with staph epi. And what the investigator here, this is done independently, wanted to see was, is there any difference between these three biomaterials? And yes, there is significant difference. The yellow stain here that you can see is actually latent infection that is still present around the implant at 3 months post-operative. There is significant infection also, but less around the titanium implant, but essentially no infection present around the silicon nitride implant. Now, it is true that the presence of an infection in an implant will hinder osteointegration, which is the purple stain that you see here, but there is significant more growth around the silicon nitride than either of the other two implants. So this was the first clue that we had that silicon nitride also exhibits this antibacterial capability. So there is a mechanism here as well. It's a very simple surface reaction. It's this equation down here at the bottom, which starts out that silicon nitride mixed with water elutes silicic acid and ammonia. And if they're in contact, the silicon nitride is in contact with the cell, particularly ammonia penetrates and degrades the cell membranes and the proteins, and eventually gets to a point where a particularly potent lytic compound forms, which is called peroxynitride. And this actually interacts with and interrupts the RNA and DNA of the cell, resulting in its overall lysis. So this is one of the early studies that was done, but this has now been replicated by people in China, in Japan, in Europe, multiple countries in Europe, and they're just kind of amazed that silicon nitride as a ceramic material would have this sort of behavior. So the advantage of this, obviously, if you make an implant out of silicon nitride, you have a material that's there which can be antibacterial. We've also demonstrated, and I won't show the slides on this, but it's also antiviral. It's also antifungal as well. So the same mechanism holds true there. So lastly, I just want to show a few slides on clinical studies. I mentioned early on the first clinical study was conducted in Australia in 1986. And there was a 30-year follow-up on the 7 remaining patients who are still living, and this is one of them that looked at. This is the silicon nitride implant here. It was a porous cancellous construct. And you can see it has very good apposition to the vertebrae, in this case in the lumbar spine. Worked very well. In fact, the authors basically stated that the study, quote, confirmed that silicon nitride is biologically safe in the long term. Remember, this is 30-year follow-up with a capacity for excellent radiographic integration. So it works very well for that particular purpose. More recently, a clinical trial, randomized controlled blinded clinical trial was conducted comparing PEEK and silicon nitride. I just show you one slide here. The outcome of the trial was what's called a non-inferiority trial. We wanted to just make sure that silicon nitride, in testing against a well-known device like PEEK, was non-inferior to PEEK, which the trial actually proved. But this is kind of a case that shows, here's one particular implant of PEEK and silicon nitride. There's a couple of things that are quite obvious. These are flexion extension radiographs. So you can see that there's basically no movement around the silicon nitride, meaning that the fusion is actually taken hold very well, and it's holding the two vertebrae together quite nicely. And you can also see the outline of the implant and also see a little bit through the implant. So it has this radiolucent behavior as well. This is the PEEK implant. So PEEK is a plastic, is totally radiotransparent. The only way you can see it is they put tantalum markers into the implant itself to see it. And actually, you can see by the movement of the tantalum markers that this particular patient is exhibiting what's called pseudoarthrosis. That means it has not fused at all, and it's just continuing to move. And of course, when it does that, it creates actually significant pain for the patient. And actually, pain is the final outcome that you actually want to look, because when these patients come in, I remember one clinical study that I was reading on this. One patient came in and told the doctor, said, please, please, I don't want to be in the control group. If I'm in the control group, I'll kill myself. Because that's how much pain he was in, associated with lumbar back pain. And so is it effective in reducing pain? Well, here's a retrospective view of this in terms of cervical devices at 4 centers conducted here in the United States with over 615 patients that shows in each center a overall significant reduction, p equals 0 in each case, reduction in overall pain scores. Now, I will have to say, if you are thinking that, okay, I can do whatever I want and I'll just get an implant later on, it'll solve me, these pain scores are still pretty high. 30% is still high. So take care of yourself first, please, because if you get up here to 70 and 80% pain, that is extreme pain for you. And it's good to get it reduced in this area, but if you can keep it at 0, that's where you want. So this was on cervical, and then a very similar outcome for lumbar pain in the same 4 studies on 359 patients. So that's it. So I tried to present for you that silicon nitride, I think, is a very unique biomaterial. It's strong, it's tough, and durable, reliable. It has good wear and chemical resistance. It's a phase-stable material. It has favorable imaging characteristics. It is osteoconductive. It is antibacterial, antiviral, and antifungal. And it can be manufactured in a whole bunch of interesting ways, including the most 3D methods that are currently being explored. So I hope that helps give you an overview, and thanks very much for your attention.